fundamental question in this field is that the existence and the deformation space for the GX structures on a given manifold or ovifold. So whether they exist or what are they grouped together. So actually, Gromov showed that open manifold admit any GX structure. So for open manifolds, we need some reasonable end conditions. The structure of the deformation space are the central questions, such things as dimension, smoothness, and so on. So this uses Ehresmann-Thurston principle that locally the deformation space is just mother the character variety. So that is, we have deformation space here, and then this is the character variety. So this is a local homomorphism generic point. So note that this has to be modified when M has n's. So these are quotients of convex domain by properly discontinuous actions when n is the BCD of the group. Of course, when this has n's, this is not strictly true, but we'll have to work with this for a while. So classify the geometry and topology of the n's arising from these ovipoles. Okay, of the n's arising from these ovipoles. So we have very little known except for the radial ends, okay, and some ends of the manifolds done by Cooper and these people. So can we classify the geometric and topological structures? So if not, can we restrict these in a reasonable sense? Okay, so geometrical means or topological means. For example, I perfect Cauchy ovipole for I bigger than equals 2. Okay, for I equal to 1, we know a lot, but not bigger than this. So we could do the same for convex co-compact structures with dimension higher than the virtual homological dimension. So BCD means the virtual homological dimension of the Cauchy group, which is just the natural dimension of the Cauchy group. So you might want to consider convex domain in higher dimensions than the natural dimension of the Cauchy group. So given the n, the reasonable structures, find the deformation spaces of the structures and these types of n and so on, and we compute the dimensions and so on. So that's what we are getting involved in. So for example, so P be n-dimensional Cauchy ovipole without n's, and P hat denote the Cauchy ovipole structure, and is bigger than 3. So what is the precise combinatorial condition tell us? It is deformable or not. Okay. Here we need some conditions on the end. More generally, we could ask for manifolds or other types of ovipoles. But this is the simplest case that we should be able to solve, I think. So for some answers now, so we have something called orderability, where these answers are doable, and also this is somewhat related to truncability, done by the Marquis, and we also have weak orderability, which shows the smoothness and the dimension at the hyperbolic points. Okay, so these are the hyperbolic n-dimensional Cauchy ovipole. So we wish to probably generalize this to all points, not just hyperbolic points. So for dimension bigger than BCD of the group, this is type of the group, there are sort of higher orderability. So we can use these to find some examples of deformation spaces. So we can kind of get lots of, we should try to get more examples here. So another thing is let we'll have the Cauchy 3 ovipole. So vertex B is B orderable if the faces of the hat can be ordered. So this is all hat, so that B is FL cap FM cap Fn. So L, M, N are ordered like this in the order of the faces, and Ni is less than equal to 1 for I equal L, and Ni is less than 3 otherwise. Okay, so L is the lowest one involved in this vertex. where Ni is the I bigger than 1, where Fi Fj is the label of label 2, so which has order 2 edges. So so Ni means that the number of sides of the higher order that meets this given phase, Fi with the order 2. So this is required to be less than or equal to 1 for this L, which is the lowest one. So then we can control the projective structure of the link of B freely. So in that case we can change these things very well. So we should work out the n-dimensional versions of this, but we haven't done it yet. So the question of Mike Davis is that can we make the projective structures of the vertices independent? Otherwise, find some maximum independent set of vertices and their relations. So for restricted deformation spaces which we worked on, the answer is not so true. Okay. So we're also interested in projective Andreev theorem. So Andreev theorem is a theorem about the existence of hyperbolic structures on convex polytope. So it has some combinatorial criteria. So let's say C is an abstract three-dimensional polyhedron and orders or ovipole and order. So here by polyhedron we mean the ovipole. So orders Nij are bigger than or equal to 2 and given corresponding to each edge Fij of the C, where Fi are the faces of C. So what conditions are necessary and sufficient for the condition existence of compact three-dimensional projective Cox-Stoll for P, which realizes C with dihedral angles pi divided Nij at each edge Fij. Okay, so we can allow the radial ends here, and also we can also work on the n-dimensional version of this. But I think it's probably get very hard after 3, or have very few examples. So cusp opening is a behavior of ideal boundary becoming a totally geodesic boundary component of dimension 2. So this is for three-dimensional ovipole. So this was first observed by Benoist and numerically by myself and Lee. So maybe there are more general behaviors, but we just work on this for three-dimensional case. So the cusp opening is that thus P hat have cusp openings to a totally geodesic boundary as sum of the ideal vertices of P. So in fact, we can ask for any hyperbolic three manifolds with cusp. Okay, so the cusp opening seems to depend on P hat and on themselves, but how? So this is related to B orderability. So this for hyperbolic three manifold case, I think the Danziger and Lee and Girutad and so on, they produce some examples, but they of course have not answered this completely. They have some homological criteria, but not completely solved this problem. So what is the global structure of the deformation space? So even for Cox-Stoll reports. So for an iterated truncation tetrahedron ovipole, the space is known to be a cell by L-Maquis or Tissot union cells, and there are some counterexamples now by many people, including me. So also, what are the possible singularities? So bending along two totally geodesic hypersurfaces give some singularity, as shown by Johnson and Wilson. So if it's smooth, then if it is orderable, it is smooth. Okay, so that's another question we are now working on. So so question of Hodgson is that let P be a three-dimensional hyperbolic Cox-Stoll polyhedron, and let P hat be its Cox-Stoll ovipole structure. Suppose the NE for an edge is bigger than or equal to 3. So is the dimension of dp P hat constant when we change NE into different values bigger than or equal to 3. So DPP is the restricted deformation space which we work on, but you can also ask for a general case of the whole deformation space. Also, we worked on projective Dehn surgery or cone angle deformation. So finally, we think that we can do RP and Dehn surgeries. So that is given RP 4 manifold with radial and diffeomorphic to T3 times R. We obtain cross 4 manifold by attaching T2 times T2. So here we remove some, cut this off by some T3, and then the point is that there's S1 direction in T3 where you can make this into a boundary. I mean, boundary of the this, and so you can add this in. So this is a standard surgery that you can do. So so here we can do cone angle deformation from 0 to epsilon, where epsilon is bigger than 0, from angle 0 to epsilon, where the singularity at the center of this you get T2 times 0, 0, and then so at this part is this part is smooth, and the singularity here is that at 0, 0 it's if you see it from D2 it will have this cone angle near 0, but it's not 0. So for which subset of G2 Dehn surgery are possible from complete hyperbolic 4 manifold to obtain RP4 structures and cross 4 manifold, convex or 2 convex or not convex. Okay, so the 2 convex I didn't explain, but you can ask me later. So Lee, Marquis, and myself did this for closed Cox-to ovipoles, probably all of these, but not for real manifolds. There are some works by Lee and Liolo. So convex co-compact of dimension bigger than this PCD or the natural dimension. So we can solve all of these kind of problem in this setting as well. So people haven't really done that yet. Okay, so let's go to the affine manifold. So an affine manifold is a manifold with an affine structure. That is manifolds with charts with the transition maps in the affine group. Or you can characterize as a torsion-free linear affine connection. The holonomy group has a linear part called the linear holonomy group. So a complete affine manifold is a quotient of an affine space by the properly discontinuous action of a discrete affine group. So we can construct many examples of cross-affine manifolds that are not complete. Of course, these are well-known constructions that are not complete, but often the linear holonomy tends to be reducible. So we do have a lot of examples here. So note that the cross-radial affine 3 manifolds were classified by Barbot and myself to be all Cypher 3 manifolds, and we all know these structures very well. So so Choi conjecture says that the closed affine manifold has a 0 order characteristic. So Sullivan proved it for complete affine manifolds. This uses a Zariski closure so that each element has eigenvalue 1. So it has a special sort of Zariski closure of the linear group. So that gives you forces some strong condition on the manifold. So Sullivan also proved it when the linear holonomy group is integral. But recently, Klinger proved it when the holonomy group is special affine, so it's much bigger generalization. Here he uses some twisted complexification. But otherwise, there seems to be really no good techniques, and so there's also related Marcus conjecture that a closed affine manifold with the holonomy special affine must be complete. So if you have a linear holonomy in the special linear group, then it must be complete. So this is conjecture. There's really very little progress. I believe that this field is quite strange with many techniques, not many techniques, as Sullivan said, particularly for this problem here. So for Ausland, the conjecture says that the closed complete affine manifold has a solvable fundamental group. So Friedrich Goldman proved it for n equal to 3, and Abel for Margulis proved it for n less than equal to 6. So this was a really big work involving many papers. So very recently myself, I proved that if the linear holonomy cannot be unresolved. This also follows by the Canary-Subalis work on the BCD of the Nusselt group. So the conjecture is that the linear holonomy cannot be relatively unresolved. Currently working on this, but this technique doesn't work there. So maybe my technique will work. So the related conjecture is that the cross affine manifold do not have word hyperbolic fundamental group. So this was open. This is open for a very long time. So let's say so for Magloire spacetime, we start with the Miller conjecture. So it says that there is no free group of rank bigger than or equal to 2 acting properly discontinuously on a affine space. So Magnus obtained the counterexample on an affine 3 space with linear holonomy in the SO21. So it is actually flat Lorentz space. And Strom and Goldman found the fundamental domain using the crooked planes. So suppose there are no parabolics, then the quotient space is shown to be tame. So tame is this interior of a compact 3 manifold by Goldman and myself, and also by the other group. People Danziger, Gertler, and Cassel. So they show that there is also crooked plane decomposition of this space. So this proves the crooked plane conjecture of Strom. So but if there is a parabolic element, then the Goldman and myself showed the tameness recently. But the crooked plane conjecture of Strom is still open for the parabolic cases. So generalization of the Magloire spaces. So Danziger, Gertler, and Cassel show that there is no exist proper action by fundamental groups of cross hyperbolic manifolds on an affine space. So they worked on some Coxeter group action, and then they were able to prove this. So Gash and Tribe generalized the Magloire spacetime to signature n plus 1 cases on the say 2n plus 1 dimensional space. And Danziger showed that the non-existence if the linear part is in the Hitchin representation, which we will show later here. So Smilga generalized the construction of Magloire's room in many dimensions here. So to solve the Outlander conjecture, we need to probably classify these actions. Okay, so let's go to the global structure of higher technical spaces. So Hitchin components are components of representation from the fundamental group of closed surfaces of genus bigger than or equal to 2 to SL and R, where the images are only consist of positive diagonal elements, as Rabori showed. So earlier, this space was introduced by Hitchin and is parameterized to be a cell for more general Lie groups. So the global geometry is still very unknown. So recently, the conjecture of Rabori turned out to be false, and one hoped to obtain a Kähler structure on the deformation spaces using this idea. But anyway, so Jung and myself showed that the volume of the Hitchin-Riemann space actually, so you have this component, but there's actually mapping class group acts on it. So if you take the quotient, that still has an infinite volume. So we show that. So in the Teichmüller case, Riemann space has a finite volume as shown by many people, but this one does have an infinite volume. So that's work. So we can go further. So Linda King found some sort of rough fundamental domain of the Teichmüller space under the mapping class group action. So we can probably try to generalize. And we can also try to compactify the Hitchin components. So this is actively researched by many differential geometers and legal theorists. However, this has a really big, very difficult issue. So, so the final part is on the surgeries on geometric structure. So First of all, classify all possible topological surgeries on orbicals. So perhaps this is done already, but I think it's not that well known. So if the orbipole has GX structure, is it possible that the surgered orbipole has a GX or some other G prime X prime structures? So when are these possible? So first we need to have more sort of examples here. So tool here is so classification of geometric structures, and also Cooper dancing or Winhard did some work in transitions in geometry. So these might help. So this area didn't seem to be well researched at all. So we had some experience with projective surgery here. So here are some references that you can look up to if you are interested in this kind of topic.